guy, then I'm not getting averaging effect, which means my variance is large. So question is, how do I do that? So they say, okay, bias, one way to think of, let's say, variance here, variance of this, and think of this as independent, and each one of them have fixed variance. So the variance of this estimator is nothing but something like alpha square. Okay? And the bias looks something like, and again, let's assume that for the purpose of discussion, and okay, maybe not is a bad choice, but let's assume that discussion, it's a C alpha holder, which is 1, 1. Okay? So this alpha is different from this alpha, and my apologies. Okay, this is the holder one. So then the bias is nothing but alpha I bi, where what is bi? Bi is equal to rho of x comma xi of x. That is how far my ith neighbor is from me. Okay. And of course, if you have generic alpha, then you will put rho alpha, rho to power alpha. Okay. So that means it's what I really want to do, I want to minimize my bias and variance. So that means that given my observation and everything, I want to find out, minimize summation alpha I square plus summation alpha I bi, and I think if I consider this version, maybe squared, I don't remember. Anyways, so that was what they did, and then they said, well, you know what, actually I'm going to set this square to be 1 rather than that to be 1, because I want to keep my variance fixed, and I want to minimize just this subject to that. Okay, and let me go and find the right choice of alphas, because later I can rescale it if I want, but so let me do that. They wrote down the right appropriate dual of that. Dual is very clean form, and effectively for that, the following answer comes out. Alpha I, or optimal answer, alpha I is proportional to lambda minus beta I plus. Okay, so there is some lambda that exists. Okay, and the alpha, the optimal thing, is proportional to this. Okay, that's a large multiplier for the constraint. This constraint, or this constraint. Yeah. Okay, good. All right, so that means that at least there exists some k star. Let's call it k star. So let's say we have betas. Betas are ordered like this. So beta 1 is greater than or equal to no, what is it? Small. Beta 1 is less than or equal to beta 2, less than or equal to beta n. This is the farthest, this is the closest. There is some k star, let's say some k star here, with beta k star and beta k star plus 1. Lambda belongs here. Okay, so before lambda is larger than these betas, and hence these alphas will be non-trivial. This and beyond, everything will be 0. Okay, so there is a cutoff, and that cutoff is proportional. Okay, so far so good. Right, so now the question is that how well does this do? Okay, let's say so we go back to our original setting, say holder setting. How well does this do with this choice of alpha? And take n given large enough. Okay, so I decided to take the easy way out. Let's take this sort of a very silly representative toy model, and here is a simple analysis. Okay, but I believe that sort of that has enough into it. So let's say 0 is my target x, therefore which I want to evaluate things, and the observations are 1 over at 0.1 over n, 2 over n, so on, and let's say n over n. Okay, and I've got uniform distribution. Okay, so this is kind of a proxy of uniform distribution, and I'm just taking this x, and now I'm asking that in this setup, if I applied this algorithm, what would come out? A little bit of calculation would reveal that the k star that comes out of this has scales like n raised to 2 by 3. Okay. It's a little bit of calculation using this and that, so I'm going to avoid that. But this is what k star comes out. Okay, so it's okay, fine. Now what? Because in some sense, there's no epsilon here, right? The algorithm doesn't have epsilon. Algorithm is trying to choose the best epsilon, or given n and given setup, it should find K so that it optimizes the epsilon. Okay. So we can go back to our world and say, okay, fine, let's see what happens. Well, it all depends. So are you sort of getting the optimal rate or not, right? So actually, let's go back to this one. We did that calculation, right? And again, as I said, this is suboptimal. So if D equals to 1, alpha equals to 1, then if D equals to 1 and alpha equals to 1 for a given epsilon, K should be like 1 over epsilon square, and N should be like 1 over epsilon cube. Okay? So if K and N satisfy this conditional simultaneously, then you get epsilon. Okay. So that means that this suggests, seems form. Does everybody see that? Pretty remarkable, at least in a toy case. Well, so again, so here assumption, as you pointed out in their work, right, is that actually you know the Holder constant. Because now question is that can we know, maybe potentially, right? Let's think about this. So for example, you have given me lots of observations, y1, y2, yn, and you also with that gave me lots of observation x1, x2, xn. Okay? For this, I can create n choose 2 data points. Okay, and let's call it n choose 2 data point as zij, which is equal to yi minus yj. Okay, and let me do this one, or whichever. Okay, and then I will do let's say zij and theta ij, which is rho of xi xj, right? Well, now if you believe in polynomials, then at least given I can fit it. And then I can sort of find out what would be reasonable bound on my Holder constant. If I have that, then I can go to this, and then I can sort of start solving that. But yeah, so again, I have not sort of gone through the calculations of how much data point you need, what sorts of conditions, but at least there is an approach. So I mean, yeah, Holder is a little strong, but if all I'm assuming is some kind of bound on Holder condition, I think it should be okay. And this is robust to upper bounds, and so as long as I have a reasonable upper bound. Maybe I'm weak on lower bound, but that's it. Yes. Good. So lambda is, yes, I'm not writing now, I'm becoming lazy. Sorry about that. So, so there's a primal problem I wrote down. Then there will be with squared alpha I square equals to 1 constraint. I will put it, I will dualize it. Corresponding dual variable is lambda. And that for optimal primal dual. Okay. Right, so I feel sort of this is a promising approach. The things that needs to be done is, okay, just after a little bit of bookkeeping and making sure that you can actually get the right estimation of Holder thing with reasonable amount of data and not too much data, analyzing this type of algorithm. Okay, and in particular, this was the toy model. Toy model suggests that it does extremely well, but toy model is toy model. Of course, there'll be perturbation even if I have uniform, and so it should be robust. But again, losing steam for that problem. Yeah. If you're indeed sort of your problem had that structure, potentially you might, because in some sense, what this is doing, right? See, this is actually capturing the whole proxy. So if you knew this really well, then actually you would do really well by actually using the precise betas rather than just bounds. Yeah. Oh yeah, so I skipped lots of calculations. They're simple calculations, but they're there in the book. There's some work. They're very simple calculations. Okay, so now I want to move to the second question. The first question was that how do we choose K? So again, so if we this, we did this, we did this, we are here, we did this. Now comes computation. So computation, let's think for a second, how much computation do we need? So I've got n points. I have K as a choice of my neighbors. If K is fixed, let's say 1, and I want to find the one nearest neighbor, I need, if I don't have any clever data structure, I need to do comparison every time I get a new query point and do n operations. If I have K of them, there are clever ways people do it, but let's say sort of for simple purposes, let's say it's K times n. Okay. Now that's a lot of work, right? Because then so you have lots of data points and lots of calculation. You don't want to do that. The question is that, is there a way for you to have a data structure so that every time a new point X comes in, K nearest neighbor come back to you in time, or let's say one nearest neighbor comes back to you in time, which is scales less than n, say square root of n. Log n would be ideal. Constant would be the best thing you can do, but then that's not hopefully feasible. Or sort of there's sort of, let's say, algorithm gets sort of log n also. So you can do n is the best you can do in sort of instance by instance. That is, I give you n points now, and I give you new query point 1, then you have to do n. But if I already told you that these n points have been there, because this is a prediction, so I have already, the quotes and quotes, learned my model. So maybe I need to build some kind of index cleverly, so that when a new point comes in, I can quickly find out which are my K neighbors, and then based on that, I can decide what to do. All the for no. So really, let's say I want to do predictions with this. What would you win? And you say, here is my feature. I say, okay, good. I've got these endpoints that I have training label available. I'm going to go and find 3 nearest neighbors for your feature out of these n things. It'll take me, if I'm naive, it'll take me 3 times n amount of computation to find those 3 neighbors. Okay, and then I will do averaging and I'll give it back to you. That means that every time I want to do single prediction, my computation is scaling linearly with amount of data. That's terrible. So what I want to do is somehow build a data structure so that I pre-store these endpoints in such a way that whenever any new query point comes in from, let's say, my support or whatnot, I can go and find that very quickly. Of course, it should be the high dimension. So the first most interesting take on this after post office problem that was Knut posted was done by Bentley in 1979, and he designed what's called KD tree or K-dimensional tree. It's a beautiful object. So if you have not seen it, I will describe you right now. Okay, I'm going to describe you in words, given the time and okay. So let's say you have endpoints. All endpoints are in D dimension. What would you do? Okay, here what I'll do. I'll take any one dimension, my favorite dimension. Okay, and I will say, in this dimension, I'm going to project all endpoints. Okay, and I'm going to find a median. Everything on the left of the median goes to the left part of the tree. Everything on the right of the median goes to the right part of it. So slowly, what I'm doing is I'm building a tree recursively, so that as I traverse through that tree, I'm actually reducing the number of points in that subregion. Okay, so effectively, right now the root is entire region. Say left and right along dimension 1 as per median. So half left, half right. It recurs. So clearly, given the way I'm doing it now, of course, so how do I recurse? Well, first I choose dimension 1. Now I'm going to choose dimension 2, then dimension 3, and so on. I keep rotating. That's how KD tree is built. Okay, and if I keep doing this at each stage of my tree construction, I'm fully balanced, roughly speaking. Which means that if I have n points to begin with, I'm going to go down log n depth. Okay, each one of them has same number of points. If I went down all the way, I'll have only 1 point. I don't need to do that. I can stop at some constant number of points. Okay, and I'm rotating through this, and that's all that is there. which means that building the index is n log n amount of operation, because at each stage I'm trying to find the median. Now it's an interesting exercise. How do you find median in linear time and not n log n time? Okay, this is like one of those Google puzzle, Google entrance puzzle. So in any case, so that's what you do. So n log n operations you do, and you are storing linear amount of data effectively. It's a beautifully efficient storage, efficient insertion. Okay, query time. How is query time? Well, take the point, keep going down the thing, and find the leaf and find the closest thing, right? Exactly. There is a catch. So if that was the case, then I won't be talking about that, because then the problem would have been solved in 1979. The problem is that, no, this is not true. The reason is that when we partition things, right? Effectively, if you think of this space, what you got is you got this small cell in which you ended up. But what if in that cell you are ended up on the boundary, literally on the boundary of this side, and there are so many points on the other side of neighboring cell on the boundary, while all the points in this cell are like far away. Okay. So what that means is that you cannot, what you have to do is that whatever cell you end up, in D dimension you find all the neighboring cells for that, and then go and search from them also. Okay, how many neighbors do you have in D dimension? 2 to D, exactly. So that's the curse of dimensionality. And that's the, so if your D is really small, life is great. If your D is not small, then there's a problem. Sorry? Well, linear, right? Because we just discussed the silly algorithm. In the worst case, if you want to find nearest neighbor, it can't be worse than n, because you can just do. Of course, yeah. So this is the, if D is fixed, this is how MATLAB, for example, implements it, and so on. Okay. Now, if D is large, what do you do? Okay, so first one would say, oh, maybe what I should is, if I've got n points, let me reduce the dimension of them. Let's do Johnson-Lindenstrass, and then life would be great, because I got any n points, any metric, I will, roughly speaking, then I will get to log n dimension, right? Not so fast. It's log n times 1 over epsilon square. Right? If you have log n times 1 over epsilon square, 2 to power of that is n to power 1 over epsilon. That's way worse than n. And remember, n is the best thing you can do. So this is a hard problem. This is not an easy problem. Okay, so that means it needs cleverness. Okay. Now, there are a whole stream of work that folks have done which say that, well, you know, my data might lie in high dimension, but actually there's a low dimensional thing. Like, for example, what Hari was talking about in his talk implicitly. Is you might have very high dimensional data, but actually it might live in low dimensional manifold. Is there a way to exploit that? And there is a stream of work that folks have done, not fully complete, it's far from complete, but there's aspects of that that people have done, and they've argued that maybe there is a way to actually build KD tree-like thing without having a suffering from curse of dimensionality in some. If you are a computer scientist, and if you look at these kind of things, you say, well, the exactly counter example that I explained is worst case. So one way to get over that is randomization, which means that instead of doing partition along the this and that, why don't I choose random projections or random lines or random planes to do partitions? So there will be random partition tree. It works beautifully well in practice. Like there are many open there that use it, but there's no analysis for that. So if you're looking at something really interesting to analyze, go bananas with random partitioning tree. Well, sort of random partition tree, their paper, if you look at sort of this there, it's kind of a no guarantee. Okay, I mean, yeah, it's better than nothing. It is non-trivial. I'm not saying it's trivial, but I mean, yeah. So point is, it's not settled. There are covered trees and few other things. There are things like Kargar and his former student, I forget his name. They try to do it using the doubling dimension view and so on and so forth. But again, they're all sort of, they're not elegant. The most elegant thing that is there in this topic is what's called as locality sensitive hashing. That was introduced by my colleague Piotr Indit during his thesis with his former advisor Raju Mutwani. So I was hoping to go through that. So let me sort of at a very high level sort of describe what the idea is and not go through the details. And then I will go through that last piece a little quickly. Okay. So locality sensitive hashing says the following. Okay. What you want to do is that you have to, exact is hard. So you have to go up to approximation. If you have to go to approximation, what you would say is, well, I've got 2 points x and x prime. I'm going to hash them to some lower dimensional space where if these two things are close in distance, their hash will match. If these two things are far in distance, their hash will not match. Okay. Now again, having that is very hard. So what you would do is that you say, okay, what I'll do is that I will design a version of this where if 2 points are close to each other in terms of their distance is less than or equal to some capital R, then their hash matching probability is higher than some P1, let's say 0.51. Okay. But if their distance is larger than C times R, where C is some, say 2R, then the chances of their hash matching is less than 0.49. Okay, so there's a small gap I have created. One way to think about how does one do that, suppose you have, there's a simple example I had. Let's do that. It is illustrative. So suppose you're thinking of a setup where you have all your x is this. Okay, so it's a Hamming cube. Your x's are coming from this, and the distance you're defining is nothing but Hamming distance, whether xi equals to not equals to xi prime. Okay, just Hamming distance. And now with respect to this Hamming distance, we want to define this simple, at least simple primitive of locality sensitive hash. Very simple. Here's what we'll do. We'll define a family hi of x equals to xi. Okay, and for I in n. So this is h1, h2, hn. Now what I'll do is that I will do random hash by choosing which coordinate to choose for my hash. Okay. Now what is suppose I've got x and x prime. Okay, what's the chance that the hash will match? Well, probability that the randomly chosen index will match, that is, this random hash for x and x prime will match, is precisely equal to 1 minus 1 over n rho of x prime, right? What that means is that if this quantity is less than or equal to r, the probability of them matching, so if the probability of these guys matching is greater than or equal to 1 minus r over n if the distance is less than or equal to r. If distance is greater than or equal to c times r, say 2r, then this is less than or equal to 1 minus 2r over n, right? So now I've got a gap, small gap, but gap. Okay. And now the whole cleverness comes in taking this and somehow what I would call amplify an index. Okay, and without going through details of any property, I'll just give you the construction because construction is very straightforward. So what you do is that you take x and you create a matrix. Okay, a matrix of let's say length d prime here and L here, and each entry here, let's call it hij of x, is nothing but a randomly chosen hash from that family. And the idea is that these are different L buckets. When your new x comes around, you go and look at all the points that match you in each of the h buckets and find the nearest guy in that. And the claim would be that, well, look, if there is at least one bucket in which nearest guy is there, you will find it. And if x and x prime are too far from each other, none of the buckets will match. Now, what happens is that when you do a big d prime like this, and you call this bucket, and you want to match everywhere, your chances of matching reduces, right? Because you have to sort of match each one of them compared to that. So this is kind of, is reducing your chances, but asking for every possible bucket increases your chances. And you've got to choose the right D prime and L. And when you do that right, and you argue that somehow everything works out and balances out and so on and so forth, you get that for reasonable distances, the plus phi, the query time scales like phi, where phi is nothing but the log of the ratio of, let's call this as p, this probability is p1 and this probability is p2, then log of 1 over p1 and log of 1 over p2. And with a little bit of calculation, in this case, you would argue that this is like 1 over c, where c was the factor loss you cared about. And as the state of art holds, the best phi you can achieve through all of these things, the scale is like 1 over c squared. Right. So I say, if you have c, you are happy to sort of do constant factor approximation of square root of 10, then the amount of query time will be n raised to 1 over 10. Okay. The error you will have is square root of 10, say roughly 3. And storage would be n raised to 1 plus 10. And this is the best you can do. There is nothing better you can do because there are very bonds that exist. Anyway, so that's this type of locality sensitive hashing. There's a really interesting things going on again right now because many of these hashings, the way I described, they're data independent. The question is, can you design data dependent things? And then sort of there's a very nice algorithm that came out from Jonathan Yedidia and his co-authors a few years back, which it's called Boundary Forest. It's very neat data structure, but there's no theorem that's known about that. So if you are interested, again, that's a good place to sort of look at. All right, yes. Oh yeah, it's fully worked out. There are a bunch of surveys that if you want to sort of read, I think Cyril Harpeled and Indic had written something in 2012, and there is a more recent version of survey. Think of Bloom filter as a starting point. All of these things have beautiful connections. I mean, these things have connections. Okay. I'll sort of refrain from. Okay, so last thing, the